All right, so hello everyone. I'm Ode, and today I will be presenting my work about parallel variational integrators on force systems and Lie groups. So my idea with this presentation is to give hopefully some kind of visualizations and some explanations that help to understand the thesis in a kind of supplementary material, and are also hopefully interesting to the audience that might be less familiar with the paper. So, I'll start by reviewing the variational integration framework around Lagrangian geometry. Then I'll talk about the parallel algorithm that was introduced by my supervisor and collaborators. And then I'll talk about the work that we did in the thesis in extending it to force systems and to Lie groups. Let's start with Lagrangian mechanics. Many physical systems, everything from pendulums to robotic arms to electrons to black holes, can be defined using a configuration manifold, which is a smooth manifold that represents the possible states of the system, and a Lagrangian that encodes how these states evolve. With the Lagrangian being a function from the phase space, the tangent bundle, to a real number. Let's see how this works with the pendulum. So the configuration space here is the circle, a smooth manifold, where the position along the circle indicates the angle of the pendulum. And now the Lagrangian also acts on a tangent vector, so really we have for each point an extra R1 degree of freedom. That is to say, the dynamics of the system are not determined on the circle itself, but rather on a cylinder, which is the phase space of this pendulum. And on this phase space, the Lagrangian defines a flow. So it says how each point in DQ evolves over time. And this flow is very important. It encodes all of the dynamics of the system, and it has also important geometric properties that we are going to see shortly. So, well, firstly, if we color the manifold via energy, we are going to see that the trajectories, the Lagrangian trajectories, form level curves of the energy, which is a way to say that energy is conserved. This is an application of the well-known Netter's theorem that says that for each symmetry there is some kind of conservation law. So here we have time symmetry like in the Lagrangian, so we get conservation of energy. Another important property is symplecticity, which can be understood as small areas being conserved as you move along the flow of the Lagrangian. This again gives you certain properties, such as that trajectories in phase space will never collapse, and it's actually a stronger version of Liouville's theorem that says that volumes in phase space are conserved. Now, where does the Lagrangian come from? As you probably already know, Lagrangian trajectories come from the critical points of the action, which is Hamilton's principle, where the action is the Lagrangian of the integral of the Lagrangian. And from this, we can derive the well-known Euler-Lagrange equations that all physical trajectories must satisfy, and is what defines the flow that we saw before. Now, the problem with these equations are very important because they give you your equations of motion, your F equals ma, but the problem is that we often solve them numerically, and when we solve them numerically, we forget about the geometry behind these equations. So, for instance, they might not conserve energy, so we might see that energy keeps decreasing spontaneously for long-running simulations. But we can actually do better. So this is the continuous formulation of Lagrangian mechanics, but we can also formulate Lagrangians discretely, where instead of thinking of a point and a vector, we think of two nearby points. And in this context, a path becomes a list of points, the action becomes a sum over these points, and the critical points of this action become the discrete Euler-Lagrange equations, or del Forsort. And notice that these equations have all of the conservation properties of the continuous formulation, but they can also be solved exactly up to like floating point precision, because now we have just a list of points. So of course, there needs to be some kind of catch, because we all know there is no such thing as a free lunch. And indeed, the problem is that an exact discrete Lagrangian needs this Q01 path, which is defined as a solution between Q0 and Q1, which is just as hard to calculate. But the thing that we can do, the clever trick here, is that we can define an approximation of the exact discrete Lagrangian using some quadrature rule. And this approximation, well, it is still an approximation, but it is also a genuine Lagrangian system that has all of the conservation properties we care about. And that's really the main idea of variational integration. We discretize the principle instead of the equations of motion. Now, let's see how we can actually compute some solutions using the parallel algorithm that we are going to expand upon. So the parallel algorithms start, of course, with the discrete Euler-Lagrange equations. And we are interested here in boundary value problems, meaning that the start point and the end point are fixed as data. Now, since we're going to start with a guess, so we're going to call whatever this happens to evaluate to the residual Rk, the residual at node k. The idea of the algorithm is to find a better approximation by noticing that the residual at its node depends only on itself and on its neighbors. So we can use this to just calculate what value for a single node will make its own residual 0 based on the current value of the neighbors. And we're going to do this step for all neighbors at once. This is the idea of the Jacobi iteration. We have parallelism over time. Of course, since the neighbors changed, probably we are not going to get the solution, but under the correct conditions, we're going to get closer to a solution. And the way we can actually compute what value will make its own residual 0 for a node locally, we do a Newton step, which is simply taking the residual and finding where a linear approximation of this algorithm, of this function, will be 0. Now, the overall method, as you probably already know, is called Jacobi-Newton because we have this Jacobi and this Newton step. We can see here an example in action of how this works. So we have a start point and an end point, and if we let the algorithm run, we're going to see that it converges quickly to a parabola, which is exactly what we expect in a free-fall example. Now, of course, it's always important to talk about the convergence of these algorithms. So in our case, the central piece is this, the Hessian of the discrete action. And namely, the main idea is that if the Hessian is positive definite, we have local convergence. This is a nice condition, except that it can be hard to calculate because, checking the positive definiteness of a matrix needs O(n) cubed steps. But we can actually evaluate the structure of this Hessian to find a better condition. So, because of the locality of the del equations, we actually find that the Hessian is block tridiagonal. And not only that, but its block in the tridiagonal matrix is each of the second derivatives of the Lagrangian, evaluated at different points. The diagonals are the straight derivatives, and the off diagonals are the cross derivatives that remain. And actually, we can think of the global Hessian as being composed by a bunch of local Hessians that are just the Hessian of the Lagrangian evaluated at different points. And with this, we can state the convergence criteria better. So, namely, the algorithm converges if the Hessian is positive definite, but we can also say that the global Hessian is PD if all of the local Hessians are PD too. And now, this condition is quick to check, it is linear, but it is conservative in the sense that many convergent systems do not necessarily pass this condition. So that's why we have an even better condition, which is that if and only if these recursively defined matrices are positive definite, then the global Hessian is positive definite and we have convergence. That's all we need to know for now for the algorithm. The contribution of the thesis is in extending this algorithm to non-symmetric systems, such as force systems, and to non-vector space configuration manifolds. Let's start with force systems. So, the force system formulation is an alternative Lagrangian formulation where instead of having the Euler-Lagrange equations, we are going to add a force here, where the force is defined as a fiber-preserving function from the tangent bundle to the cotangent bundle. And then, given this formulation that allows us to model non-conservative forces such as damping, we can follow as before and compute discretize the principle, and we are going to find that we get almost the same thing as before, except that now we have some extra forces. And notice now that we have two different forces, because actually we need two forces to model this kind of function in a discrete manner properly. Now, the algorithm itself is very easy to modify, because we just change the expression for the residual by adding the forces, and that's it. The problem is in checking convergence, because the Lagrange-D'Alembert principle that we're using here is no longer a stationary action principle. So we don't have any Hessian to speak of. We can get an analog essentially by differentiating the residual, but the problem is that this analog is no longer symmetric. As where before we had some nice symmetric matrix, now the off-diagonals have the different force terms, which make the Hessian or the matrix non-symmetric, so we cannot say anything about positive definiteness. There are some analogs we can talk about. So, for instance, there's this condition here that says essentially if locally the diagonals somehow dominate the off-diagonals, then we get local convergence. And essentially this is the analog of the local Hessians being all positive definite. And I guess it is a good analog because it is also very conservative, meaning that many convergent systems do not necessarily pass this condition. Of course, we would like to say some global analog here, which would be this condition, and it seems to be a true statement. It seems to hold for all systems we tested, but I couldn't quite figure out how to tackle proof for it, so it is still open in that sense. But there are other kind of conditions we can give. So, for instance, this is an interesting condition that this bound on the size of a force we can add to a non-convergent system and keep it convergent. So first we saw it exists, then we give a bound. This bound is again kind of conservative. So really, if you have kind of a system in front of you and you want to check numerically if it converges or not, it might be easier to just compute this Jacobi iteration matrix and check its spectrum. This is kind of a more practical approach numerically, but this can be more useful in a more analytical context, such as saying how much damping you can add to a system. Right. And here we have, again, a quick example of a force system. Now we have a parachutist that moves through a wind field, and if we let the system evolve, we see that the parachutist has to kind of move, overshoot the trajectory to be carried with the wind to the target. And now, finally, let's talk about Lie groups, which is honestly my favorite part, so that's why I have a lot of time for it. So, what is a Lie group? A Lie group is a smooth manifold where we can only assume some kind of group structure to it. So the classical example is SO3, the group of 3D rotations. We can also think of SC3, the group of rigid body motions. And really here, the idea is that since you don't have this vector space structure, you almost have to forget everything you know and really think through each step and think if it is well-defined or not. Classic example, in SO3, for instance, rotations do not commute. So if we rotate one way and then the other way, we get different results. And this alone describes actually the vector space structure in SO3. In terms of the algorithm, the problem is the Newton correction, because in the vector space, we are adding a tangent vector to a point, which is not well defined in a general manifold. What we have to do instead is compute a correction in the Lie algebra and then apply it via retraction. So let's try to unpack what this means exactly. We're going to take a manifold. So technically, a sphere is not a Lie group because it does not have a group structure, but it serves as a stand-in for a curved surface with a translation action. And the Lie algebra is just the tangent space at identity. And if we zoom in and we take an element of the tangent space, the retraction is going to associate this tangent vector with some point in the group, where the group action of this element somehow corresponds to the action that is associated with the tangent vector. And really, there is no one true retraction. We can, for our purposes, any function, any smooth map that has the correct signature that maps 0 to not doing anything, so the identity, and that is linear around the origin, can serve as a retraction. So the classic example is the exponential map, but for matrix Lie groups, the K map might be more convenient. Really, the point is that we have this local association between the tangent space and the group. And actually, the reason why we care about groups specifically is that they give us a canonical way to talk about all tangent spaces using the algebra. This is called the trivialization of the tangent space. So, namely, I often have some correction, some direction, some correction in the algebra, and I want to apply it to a point. Well, I can push it forward using the differential of the left translation operator, which kind of does exactly what you think it should. It moves the vector forward. And conversely, or contravariantly, if I have a covector at a point z, which we can think of as a linear form on z, so some kind of computation on z, I can apply it to a point in the identity, to a vector in the identity, if I just push it forward first. And this kind of aggregate machine is the pullback of the differential of the covector, and it gives us a covector at the identity. So that's the name of the game here. We push forward tangents, we pull back covectors, and that way we can do all of the computations in the algebra. To see how this applies to the Newton step specifically, we're going to have here an example. So this is kind of our manifold with the residual coloring. The idea is that we want to solve the residual being 0. The solution is right there. So, analytically, what we're going to do is we're going to assume that the residual kind of changes linearly. And if we solve for this, we're going to find that we have some expression for this decay and then some update function. So the way that we can visualize it here, well, first I want to say that linearizing the residual is not the same as linearizing the manifold, which is kind of the association that we have with tangent spaces. We're not taking a tangent at the point. We are rather, the way to think about this, is that we're taking a small region around the point, and we are extrapolating how this small region looks to the rest of the manifold. This is what linearizing the residual is. And then once we have this, as you see here, we have a push forward and a pull back. So the way kind of to understand this is that we are going to move all of the computations to the algebra. So it is vaguely kind of moving everything to the algebra and computing the update there. And well, since we linearized, we didn't quite get to the solution, but we got close to it, which is the objective here. And then, in terms of convergence, in the Lie group case, we have this kind of pattern. We want to show that certain derivatives of certain. So here, for instance, we have the Lie action in a Lie algebra chart. We want to show that the Hessian of this action is the same as the derivative of the residuals in different positions, and we get this pattern where we have a main term and then some extra terms that relate to the curvature of the manifold in some way, or the change of basis essentially that we're doing. and they are all weighted by the residual. And in terms of convergence, we often care about solutions we care about values at a solution where the residual is 0, so we can all ignore them essentially. These terms all vanish, and we get kind of the results that we wanted, and they are actually identical as the vector space case. Really, most of the work here is just in working everything out carefully. So I wanted to put an example here. We have this expression, and then it kind of seems like we can almost differentiate it again to get this expression, which is kind of what we're after, except this is totally wrong, right? Because this is a function, this is a value, and you cannot just pattern match the syntax, you have to think about what everything means. The correct way to do this is actually more involved, right? So we have to think of the general expression of the derivative of the Lie algebra action, and this involves the pulled back differential of the Lie algebra chart, which is, at the end it doesn't matter, because actually if we differentiate this, which is what we have to do, we get at the solution at 0 that actually we get different terms, but at a solution they will be the same because the residual is 0. So we got almost the correct solution by doing the wrong thing, but it's important to do everything correctly. And before closing out, I do want to make kind of one final higher level observation. So this is the update in the Lie group. And in the paper, I show that if you consider the group action of a vector space, this disregards essentially to exactly the same update that we had in the vector space case. And this maybe gives us some confidence in that we did everything right, but also, why would it be exactly the same? So what I want to argue is that really these are the same because they are kind of saying the same thing. These are both ways of computing an update to get closer to a solution. Right? The vector space case is just particularly convenient because the space, the tangent space, and the cotangent space are all structurally identical. You move between fibers without ever even thinking about it. Even though nominally that tangent vector and a point are different. In the Lie group, we have to be more careful about this, but again, we use this notion of symmetry that the group encodes to actually move everything to the algebra and compute essentially the same update there. That is why we see some curvature terms, and that's also why the solution doesn't change in the end. And of course, that begs the question, what if we have some other kind of structure? And well, I would argue rather that the question here is, what is the right language to speak about these transformations that span the manifold in, for instance, homogeneous spaces or Lie groupoids? And that brings us nicely on to future work. So things that I kind of said during the presentation, there are some things in the force systems case that we might be able to find better conditions, and it actually might be worthwhile to look into different ways of finding convergence criteria, such as Galley's idea of duplicating variables. It will be interesting to see force systems and Lie groups together. So really, in terms of implementation, this is trivial, but in terms of convergence analysis, this is a bit non-trivial, but it seems doable. As I just said, other configuration spaces, such as groupoids, and finally, we can consider other kinds of Lagrangians. So probably at the top of the priority list, it will be something like constraint systems that gives us access to robotic arms and stuff like that. With all that said, thank you very much for listening.
Thank you. So, thank you. The presentation very beautiful. Thank you. And I also want to congratulate you on the report is very clear. I have to apologize because my differential geometry is very rusty and I know nothing of Lie groups, so I can't ask you clever questions about that part, but I hope Rodolfo will cover for me in that point, or even the more physical part as well. But really interesting stuff. There's a point where I don't know if I understood correctly. So you start discussing that the thing with, when you discretize your problem and then, apply, normal integration or anything, you're losing the conservation laws. And you say, okay, so we're doing the variational integration, but then you kind of mentioned symplectic integrators. Aren't they the same thing or not?
So, yes, actually there's even more confusion because there's also like geometric integration, and variational integration, and maybe also symplectic integration. So, there's like, a Venn diagram, there's some overlap, some non-overlap. Here, generally, the term we use is variational integration because the main idea is that we are discretizing a variational principle, which is the Hamilton's principle of the action. Now, it is also a way to get a symplectic integrator, right? Because the variational approach kind of gets you the symplecticity automatically, but theoretically it doesn't have to be that. In practice, from what I've seen, at least in terms of Lagrangians, most symplectic integrators are actually just variational integrators in disguise, but it can be more general. And then geometric integration, from what I understand, is the more umbrella term of using like integrators that care about some geometric property.
Yeah. So because symplectic integrators kind of force you to fulfill the Hamiltonian, I guess.
Yes.
All the time. Yeah. And you're looking at it from the Lagrangian. Yeah, it's interesting. So have you? I mean, this is out of the scope of the work. But have you compared this algorithm with non-variational algorithms to see, to say like, hey, this is like it works much better, or
Personally, I have not really done this in the context of this work. Well, technically, wait, did I have this in the end? No. I had some kind of visualization where I showed kind of a solution. No, I do have this. Yes, actually. So, yes, the Lagrangian flow, technically, is using a non-geometric integrator. It's just using like unhekuta to find the solution in the flow. So technically, that's a place where I'm using a non-geometric integrator and we get fine results because it's very small error. Now, did I, actually compare this in the work properly? Not really, because, you would have to write an alternative implementation and I was more concerned about the math. Mm-hmm. But I have seen, such as Marsden and West, there's a reference and it shows that a specific example that's kind of well known, that a generic integrator shows that the energy kind of keeps decreasing, and then a geometric or a variational integrator shows the energy steady. So I didn't prove it personally, but I saw references.
Mm. And so finally, so I know nothing about Lie groups. You are clearly very enthusiastic about them. Good. So try to sell me on this. If I have any physical problems, why would I want to? And I know nothing about the algebra or anything. Why would I want to make the effort to translate my problem into the corresponding Lie group when I have the older algorithm works well, right? I know, the boundary conditions, whatever, the pendulum, yes. But, if I have my pendulum in R,
yes,
I could work with that, with your algorithm.
Yes.
And why do I, what's the advantage of using the Lie group?
So I'm extremely happy you asked this, because this was something that I kind of wanted to discuss, but I realized, it doesn't really make sense in the presentation. But the idea is that this encodes better the idea of what exactly your valid states are in a system. So if you thought of a pendulum that maybe could wind itself, then okay, you want R1. But here, you want to be able to say that, well, as long as we don't do a full rotation, it's essentially R1. But when we start doing more than one rotation, we actually get different results. And in a pendulum, it's very easy to understand when this matters and when it doesn't. But imagine if I had a Lagrangian in a circle where we also have like some rocket ships and it teleports or something like very weird, then suddenly it would be hard to understand if you can actually trust the results or not. And an even better example perhaps is that if you had some kind of, so you can use Lagrangians to model optimal navigation problems, things like that. So you could imagine that maybe an optimal trajectory would have some object that does more than one turn to reach a point. Mm-hmm. So I almost had that in one of the examples, but actually in SO3, that's not the way it works. It actually counts rotations. But you could imagine some object where, yes, the optimal trajectory does more than one rotation to reach the endpoint. And if you used R1, you wouldn't get that because you would say, well, I want it to have exactly kind of the same number of rotations at the end, which might not be the thing you're trying to model. So really it's just, when it is often more practical to just model something, out of band and just say, well, we're just going to assume this is a real number. But if you are able to model everything mathematically, then the idea is that you get all of this mathematical rigor and these tools that work exactly in this mathematical context. So yeah, that's mainly the idea.
Okay, thank you.
Thank you. Well, I joined Pablo, of course, in the congratulations. I also like both the document, I found very nicely written, and also the presentation, of course. Even so, let me suggest you numbering the slides.
I thought about it when you said it. I was like, I didn't write them.
Yeah. Then, related with this, the use. You're given in the introduction this interesting example of the gimbal lock, right? Which I guess is related to this issue.
Yes.
In a way. And then you just go to you wish like a Wikipedia presentation of the gimbal lock phenomenon, and they provide, they suggest that's the motivation for the use of quaternions.
Yes.
Can you comment on that from this perspective? I mean, in particular for that example, maybe
So
if it helps.
I am not that familiar with quaternions. I use them, like I tried to understand them years ago when I tried to do some game development things.
Mhm.
From what I understand, quaternions also, well, if I remember correctly, I think it's unit quaternions that represent
Yes.
possible orientations, yes.
I think so.
So I think unit quaternions in SO3 should be isomorphic.
Maybe.
So in that sense, I think it's essentially the same thing. It's like a way of, like a different way. Maybe quaternions have some reason that are like maybe easier to encode somehow numerically or something. So it's more used in actual rotations. But it is the same idea at the end of the day. It's that you use a system. Well, really the problem is that a rotation cannot be fundamentally encoded in 3 dimensions in an open, in R3 because it's not a vector space because the rotations do not commute, or also because of other reasons. But yeah, so that's the idea. So we were taking this thing that cannot be really. We are taking a representation that has somehow some flaw, especially in a global scenario, and then we're taking a better representation of it, or a representation that maybe not better. I don't want to make a value judgment, but it is more useful and that does not have these limitations because it has more degrees of freedom essentially.
Mm.
That's the way I understand it.
Related with this, also, I was expecting to see, that I'm okay with that, is some of the other numerical examples you were giving, I mean, you are considering in the thesis. And I had a question about, maybe I'm not understanding correctly. There was this, okay, I think it's for both, it's figures 5.1 and 5.2 in the document. Let me show you.
Well, yeah, the one with the satellite.
Yes, okay, let me, if you don't mind, let me get this. Thank you. So I'm just looking for the figure.
This one of them is the examples.
Okay. Yeah. This is these 2 examples, right?
Mm-hmm.
My question is about the orientation of the slab.
Yes.
Is it a part of the, so this is a boundary value problem. That orientation is part of the data, both at the initial and the final point?
Yes.
That's correct, okay.
So you want to start with one rotation and with a different rotation.
Yes. Okay. And then I was curious, you were showing the parachuter.
Mm-hmm.
Have you tried, to study the dependence of the solutions on physical parameters or the relative weight of the physical parameters like the strength of the wing, the mass of the parachuter, the friction coefficient and so on?
Yeah, so I did play around with a lot of different parameters, right?
Yes.
So I checked, for instance, if you have very high wind, you essentially get that it just moves with the wind field. Or if you have very drag, it essentially moves exactly with the wind field, which is kind of not really interesting because the point is that you want to have some inertia. And then, for instance, I also I want for it to be semi-realistic, so I don't want the parachuter to jump at 5,000 kilometers an hour.
Mm-hmm.
So I did have to actually modify. So I had it. So yeah, my script I think automatically calculated the terminal velocity of a parachuter, and then it modified that a bit to make it more to have the time between getting from the start to the end to be somewhat realistic, so you get kind of realistic results. But yeah, I don't think it was, and that was anything that was very particularly interesting about seeing a lot of different parameters. I just wanted to show kind of non-trivial behavior, such as overshooting the endpoint.
And then on the other side, so to say, is there any distinguished problem in mechanics whose numerical integration could benefit really from your schemes?
So that, I guess it is kind of coming out of my expertise because I don't really use the systems. I just kind of got presented the system and said this is probably useful. And maybe this is kind of the programmer in me that's thinking this, but I always think that invariants are very important. So the thing I was thinking about is something like a satellite trajectory. You want to throw something and then you want to, maybe at some point you have implicitly assumed that, oh yeah, energy is going to be conserved, so we're going to take the energy here, do some computations, and then since the energy is the same, we're going to do something else. And maybe if you are using some other integrator, this fails horribly, and suddenly you have some inconsistency, and everything breaks down. So in that sense, where you have to, I would say generally where it is important in cases where you really care about this invariance. But of course, it's not the only problem because you might have energy conservation and then have the satellite go the other way than what it goes in real life because the system itself is an approximation. So you kind of need both. But yeah, I would say that it is important in these cases where you care about these conservation laws, and also maybe, and this is more about simplicity, if you have some kind of system where you have many different trajectories, and you want to make sure that they all are kind of kept distinct because simplicity kind of guarantees that the trajectory will not collapse. Those are kind of my ideas.
Just a final remark. Curiosity, I don't know. I was intrigued by the structure of this. Could you please show the Hessian? When you were discussing this Hessian matrix and
just further up. Yeah.
right, and in relation with when you have, I think this. Let me see. This is page 16 in the. This in theorem 3, you have these lambdas, capital lambdas.
Yes.
You have the formula here. I think. Yeah, that one.
Yes.
So that recalls very, very strongly something called the Schur complement.
Yes.
Okay. Is there really a relation with the Schur complement here?
I think so. So, the way that I realized this relation is when I was looking at how, like, if you imagine, well, what if we don't do the Jacobi step and we just do a global Newton, you would get essentially, I think it's the Bloch-Thomson or something method, and you get essentially the same thing again. I think that is essentially used in the proof of why this works, and I'm pretty sure there should be some kind of intuitive understanding of like why this makes sense. And actually, the thing is that I discovered this kind of late on in the process, so I didn't really have time to really think about it. And it's something that I didn't really like, that I thought this came out of the blue. Then I realized it doesn't come out of the blue. I think it's related to that in some way. Could I tell you exactly the precise way it is related? Right now, I don't think so. But there is some kind of relation, I'm pretty sure.
Thank you very much.
Okay, thank you.